As most of us know, there's a little bit of a spiel in the beginning that I'll go through. So thank you everyone for joining us for the 20th session of the Journey Down the Clackamas. I'm Liz Gilliam, the Restoration Program Manager for the Clackamas River Basin Council. And joining me is Todd Bartlett. He's the CRBC Board Chair, and he's assisting with all of the technical aspects of this. Before we get into the program, I'll cover a few items. The Clackamas River Basin Council is celebrating its 25-year anniversary. Since its founding in 1996, the CRBC has worked as a non-governmental group of stakeholders to protect and improve the Clackamas River Basin and its tributaries. Our mission is to foster partnerships for clean water and to improve fish and wildlife habitat and the quality of life for all those who live, work, and recreate in the Clackamas River watershed. The Clackamas River Basin Council invites applicants interested in joining our staff to protect water quality, improve fish and wildlife habitat, and the quality of life for us all. There are 3 position descriptions on our website right now for Restoration Program Manager, Communication and Stewardship Program Manager, and Communication and Program Coordinator. So check those out and send the good word along to anyone you know who may be interested. On behalf of the Basin Council, I'd like to thank our 2 gold sponsors, the Oregon Beverage Recycling Cooperative and Clackamas Water Environment Services. Todd, will we be showing the video for the recycling cooperative? And we would also like to thank our bronze sponsors, the Clackamas River water providers, the Geological Society of Oregon Country, Port Blakely, and Metro.
Sorry,
and
Liz, a little technical glitch here. I've got it coming up.
Yeah, no problem. So this is a short video from one of our sponsors.
Welcome to Bottle Drop Express, a new, faster way to return your bottles and cans. It has a state-of-the-art self-served machine and a convenient drop door. Get started by signing up for a free Bottle Drop account. Our super easy sign-up process starts at the kiosk, located inside a participating grocery store. Follow the prompts on the screen, and the kiosk will distribute a customized card and tags for your green bags. Next, purchase a roll of green bags at the counter. Stick your custom tag onto the green bag and fill with redeemable bottles and cans. Plastic, aluminum, and glass all go in the same bag. When you're ready to return your green bags, use your bottle drop card to open the drop door. We'll process your bottles and cans and deposit the funds into your account within the next 5 days. You can access your account funds using your bottle drop card at the store kiosk. Print off a voucher and redeem it for cash at the checkout counter. For more details, visit bottledropcenters.com.
All right, thank you. So thank you to Bottle Drop, and then we also want to thank our bronze sponsors. Clackamas River water providers, the Geological Society of Oregon Country, Port Blakely, and Metro. And thanks to the many individuals who have donated to support the conference. We continue to seek additional donations, which are tax deductible. So the Clackamas Basin has been occupied by Native peoples for millennia. It is originally the territory of the Clackamas, Chinook, Molalla, Kalapuya, and other peoples, and is currently recognized as lands of the Confederated Tribes of the Grand Ronde, the Confederated Tribes of the Warm Springs, and belongs to other Native peoples who may not be federally recognized. So we thank those who came before us for their stewardship of these lands and waters, and those who continue to steward them now and in the future. So we're gathered for this journey down the Clackamas to learn in-depth information about the basin and its connections to Oregon as a whole, to connect with each other so that we can support our mutual efforts to protect and improve the Clackamas River and its tributaries, and to have some educational fun. CRBC is partnering with the Environmental Learning Center at Clackamas Community College. Workshop attendees will receive a signed certificate of completion for each session. If you would like a certificate of completion, add your contact information to our Journey Down the Clackamas Conference Networking Google Sheet and indicate you'd like a certificate in the G column, and we'll forward your contact information to Clackamas Community College. Some ground rules before we start the presentation. Please keep your microphone muted, and you can keep your cameras off if you like. That helps us save bandwidth for our presenters, and also reduces the carbon footprint of the meeting. We will have one presenter today, and atypical to usually the flow of program is we are opening up to questions throughout the presentation today. So if you have any questions, please either raise your hand or put in the chat, I have a question. That would work just fine. Then you could unmute yourself and ask that question. Or if you prefer to just write a question in the chat, go ahead and do that. And we'll be fielding those throughout the presentation. And there'll be pauses in the presentation also to see if there are any questions out there. So if I miss a raised hand or something in the chat, please feel free to speak up. And there will also be a short Q&A after the presentation. And of course, as always, feel free to send chats to folks you know that are in attendance. So now I'd like to introduce our presenter. Thanks, Todd, for the slideshow. Today we have Nick Ackerman. He's a senior scientist for Portland General Electric. For the last 14 years, Nick has worked for PGE on a variety of issues, mostly related to fish passage evaluations for salmon, steelhead, and Pacific lamprey at the dams on the Clackamas. Prior to working for PGE, Nick was in consulting and worked for several clients on developing habitat capacity and life cycle models to assess the effects of various habitat impacts on salmon and steelhead populations. Nick began the transition from consulting to working for PGE by helping PGE understand the effects of elevated temperatures on fish populations in the lower Clackamas River. So now let's welcome Nick as he presents about habitat capacity, restoration potential, and other factors considered in fish habitat restoration.
All right, thanks, Liz. Let's see, I'm gonna go ahead and share my screen here. All right, can you see that okay?
Looks great.
All right, let me just slide this around a bit. Sorry, I've got to reorganize my monitor here. Okay, thanks again, Liz, for that introduction. Yeah, so the last 14 years or so, as Liz mentioned, I've worked for PGE here in the Clackamas, working on a variety of issues. But in a previous life in consulting, I dabbled in the topic that I've been asked to speak about today, and that's talking about habitat capacity, particularly as it pertains to salmon and steelhead habitat restoration. And so I do have some experience in this topic. I wouldn't consider myself an expert necessarily, but I've dealt with these concepts enough that I'm comfortable with them. And I think that, as I go through, I'll share from my experience. I've had a chance to see behind the curtain on how some of this stuff works. And so all along the presentation, I'll be kind of talking about the approaches that people take and understanding capacity and how we use our understanding of that, but also kind of be throwing in some grains of salt just to make sure everyone keeps a healthy dose of skepticism as they encounter some of these concepts, after today. So first off, just to kind of outline what we'll be covering today, we'll start with just, what is habitat capacity? I'll go over sort of a general conceptual overview. What factors determine habitat capacity? How do we estimate it? Importantly, particularly in the last 10 or 20 years, is what is the relevance or importance of water temperature when it comes to understanding rearing capacity or habitat capacity? What's the relevance of this to stream restoration? And lastly, I'll touch on application of this to the Clackamas Basin and then finally wrap up with some conclusions. As Liz mentioned, you can feel free, I'll kind of pause once in a while and ask if there's questions, so you can ask along the way, or feel free to save your questions to the end as well. So starting off, what is habitat capacity? Also known as carrying capacity. Habitat capacity is essentially the number of individuals for particular species that an environment can support. And so, aquariums provide very tractable examples of carrying capacity. It's easy to envision how, like in this example here with the fishbowl in the Oregon Coast Aquarium, how the resources available permit different population sizes. And there's some variability in the definition. Like if you Google habitat capacity or carrying capacity, you'll get a range of definitions, but they all kind of center around this concept. And you also notice that conceptually, capacity is defined as number of individuals that can be sustained on average, though it's recognized that the abundance of a population, even at capacity, will vary to some degree. So carrying capacity is an important concept in ecosystem research. It goes back to the 1950s. And in fisheries, there's really two common population dynamic models that you'll come across. And there's others that I'll talk about, or at least share examples of in a little bit. But the two main ones that really go back to the 50s are the Beverton-Holt model and the Ricker model. And I'll just kind of describe these graphs just a little bit so you can understand, because these graphs help display the idea of what's called density dependence, which is relevant to habitat capacity. And so if we look at this graph on the left here, this is a conceptual relationship between, and this is relevant, this particular graph is for, let's just say, a fish spawning population. So it's showing us the relationship between the number of spawners on the x-axis and what we call recruits on the y-axis. And recruits is essentially progeny, right? So it can be progeny of whatever life stage is of interest to you. It could be fry, if we're talking about salmonids, it could be fry, or par rearing in the summer. It could be pre-smolts or smolts, or it could be, commonly it's, when this is looked at, it's adults. And so these two different models, the Ricker and Beverton-Holt, both show that when you have a low abundance in your spawning population, you tend to get high rates of recruitment. And so that brings us over to the second graph here, where we look at essentially the relationship between the number of recruits per spawner or progeny per adult, how that changes as the number of adults in a population increases. And so this is what we call density dependence. The more adults you have, the more spawners you have, the fewer progeny you get per spawner. So very low abundances, you get a lot of juveniles produced per adult. But when you get to high abundance levels, that number of juveniles per adult decreases. And that's just due to constraints in the amount of resources available. And so a couple of things I want to mention. One is there's this term in recruitment modeling called productivity, and that's essentially how how productive or how quickly does a population grow when it has few adults. And then the other piece is capacity. What is kind of the limit on what the habitat can allow? In these two different models, the Beverton-Holt model basically says, it's the darker line here, it says that the more spawners you get, the more recruits you get, but at some point that basically plateaus off. Whereas the Ricker model includes this idea of what's called overcompensation, which says that, well, if you get too many adults, you actually start to lose recruits. You have lower numbers of progeny, and this can be due, a common cause of this would be if you had disease, for example, something that is going to reduce the number of progeny, the more dense individuals get. So as you have too many spawners, if there's a disease issue, that disease can spread more easily and it actually pulls down the number of recruits. So I think the important takeaway here though is this idea of density dependence. The more adults you get, the fewer recruits per adult you get in return, and the idea of capacity, that at some point you can add more and more spawners, but there's a limit on how many individuals the habitat can sustain. But in practice, these clean theoretical models can be quite messy. So this is an example from the Clackamas of our winter steelhead population upstream of our hydro project on the Clackamas. So these are essentially, adults counted at North Fork Dam, and then the recruits, their progeny that come back years later. And this level of uncertainty here, so each point is basically, in a given year, we had this many adults, let's say 600 adults, and we had 1,500 recruits from that. And then the kind of cross mark is the uncertainty around that estimate. And you can see this gets quite messy. And that's common. And that variability can be due to a host of factors that include, one, imperfect data. So there could be uncertainties in the age structure of your recruits. There could be uncertainties in how many of your fish before they returned were taken out by harvest. That has to be accounted for when trying to determine recruitment. Sometimes it's as simple as just uncertainty in your abundance measurement, right? Like on the Clackamas, we're fortunate we have our adult sorting facility at PG's dams, and we have a pretty finite estimate of the number of fish passing upstream, a pretty certain estimate. But if you're in a basin where you're relying on, like, let's say red surveys, for example, one, knowing how many reds are in the river can be difficult, but then two, expanding that to sort of estimate how many adult spawners are out there gets even more difficult. So there's a host of ways in which variability can be introduced. And there's also just variability in what limits capacity from year to year. So what is limiting capacity can be different from one year to the next. For example, if you're in a basin and you have a drought year and there's high temperatures, perhaps those temperatures themselves are limiting capacity in that particular year. Whereas during let's say a wetter and cooler year, it might be some other habitat factor that is limiting capacity. So already we've kind of touched on two challenges with this concept of carrying capacity. So the first is that there's sort of a paradox in the definition of carrying capacity. And this quote from Sayer 2008, I think captured this pretty well. And he said that if carrying capacity is conceived as static, meaning that it's fixed, it's theoretically elegant, like I showed in the previous recruitment curves, but empirically vacuous. But if it's conceived as variable, it is theoretically incoherent, or at least question begging. So as they point out, there's a bit of a paradox in this idea of carrying capacity. The second issue, as pointed out in this graph here, is there's just challenges with empirical proof. Even with perfect data, variability will abound, and rarely is there perfect data. But regardless of these issues, carrying capacity is an important concept in the ecological literature, and we can find empirical evidence of carrying capacity even in the Clackamas Basin. So what I mean by that is, for example, here at PG's hydro project, we count the number of adults that were passing upstream in North Fork Dam, and particularly in the beginning about 9 years ago, we have pretty good counts of the number of of juveniles that come downstream through the project. And one thing we've seen is with steelhead is that really, regardless of how many adults we have put upstream in the last 9 years, and you can see we've ranged anywhere from 800 or so up to 2,400, that we tend to get 35,000 to 45,000 smolt progeny out of those adults. And so even though we're seeing, you know, a threefold difference in adult abundance, we're only seeing, you know, juvenile abundance vary by plus or minus maybe 10 or 15%. This past year, we only put up 662 adults. So we'll see, you know, that will be the new kind of low point on this x-axis. We'll see if we finally come out with fewer smolts than that. But the idea is that we seem to be at capacity for juvenile rearing in the upper Clackamas, that our capacity is somewhere in the 35,000 to 45,000 smolt range. And then when you look at this a little different way, so this is, recall this graph in the upper right from earlier, where we have how many progeny per adult do you get as the number of adults increases. You expect that to come down. So the more adults you have, the fewer progeny for adults. Well, that is in fact what we have been seeing for both upper Clackamas winter steelhead and for our coho in the upper Clackamas, that the more adults we put upstream, the fewer smolts per adult we're getting coming out. So there definitely is, you know, despite the challenges with the carrying capacity concept, of which density dependence is part of, there definitely is evidence out there that it's not all theory. There's evidence that supports it. We can see it in our own watershed. So why is this important? In my experience, the idea of carrying capacity is used commonly in a few different manners, at least in fisheries. It's an ecological concept and it applies across disciplines, but my experience obviously is in fisheries. And so first place you'll see it come up is like in population viability analysis used in ESA listings, recovery planning, etc. I have seen it used to determine realistic reintroduction goals. So if a new passage program, in particular, I can recall instances where new passage programs have been put in at hydro projects where there was not previously passage, and they'll use modeling techniques to try and estimate what is the carrying capacity of the habitat upstream of the dam, so they have some idea of what their expectation is for population sizes, eventual population sizes upstream. It has a long history of being used to manage fisheries and identify harvest targets, such as optimal sustainable yield. It's been used to determine the impacts of certain actions on fish populations, environmental impact assessments, looking at water management, habitat changes, even something like climate change. And lastly, the place you'll commonly see it used is to determine the expected benefits from restoration actions or to prioritize restoration alternatives. And I'm not going to go into detail on each of these except for that last bullet, how it's used in restoration actions, which I'll get into in a little while. So before I move on, are there any questions at this point that anyone would like to ask? Liz, maybe if you could help me out and flag me if somebody raises their hand or something.
Right. I did get a message from Bill Monroe. Bill, would you like to ask the question? You want me to read what's in the chat here? Bill asked about the capacity for the upper Clackamas winter steelhead. Is it possible to improve that capacity? And did your graph take into account the fire and Fish Creek damages?
First question is theoretically yes. I mean, that's the idea, right? That if you can improve the quality of the habitat or the quantity of the habitat, you can improve capacity. Making that happen on the ground could be more, particularly making it happen to the extent that it's detectable could be more challenging. Did the graph reflect changes from the fire? This graph is based on data through this last spring's smolt collection period. So smolts that outmigrated in spring of 2021. So yes, those fish would have been, rearing as 1- and 2-year-olds in the upper Clackamas during the fire. I can't recall offhand which of these dots is that. If we're going to see an impact up there, I think it would be more likely to start to play out beginning next spring is where we would start to see it.
That's all I see for questions right now.
Okay, I'll move on and we can check in again later. So next question, I guess, obviously, is what determines capacity? And so fundamentally, capacity is determined by the quantity and quality of habitat as it relates to the needs of the species. By definition, then, the same habitat has different capacity for different species. So if you want to think about differences in, okay, what does water quantity and quality mean? Examples where water quantity is dictating, where that question might be relevant is, basins where maybe there's significant water withdrawals. You want to look at the impacts of drought, or I think quite a intuitive one is if you're removing or a new barrier is introduced. Obviously, that changes the amount of habitat available in the basin. So there's a pretty tangible effect on quantity there. Quality examples might be if there was just a general loss of habitat complexity, such as removal of large woody debris, a stream channel has been channelized, maybe a sediment supply has been interrupted, or there's been an influx of fine sediments for some reason. Those would all be examples of changes in habitat quality that might affect capacity. If we just kind of touch briefly on this idea of different species having different capacities and different habitat requirements, pretty straightforward example of this would be different habitat requirements for pink and chum salmon on one hand, who spend a pretty high percentage of their life cycle living in saltwater, whereas species like Chinook, coho, and steelhead do have a much higher percentage of their lifespan spent in freshwater. So these make important differences that determine what the limiting factors are for each species. So for example, if you look around the literature for papers that talk about habitat capacity for chum salmon or pink salmon, you'll find that they tend to focus on, there are instances where they look at spawning capacity, but more often you're going to see that they're looking at what's our capacity limitations out in the ocean. And so like this paper here, they were looking at capacity of chum salmon in the eastern Bering Sea and looking at how sea surface temperatures affected their prey availability at sea. So if folks aren't familiar, chum and pink salmon obviously spawn in fresh water, but soon after fry emergence, they just kind of drift straight to the ocean, whereas the other species, coho, Chinook, and steelhead, tend to spend a much more protracted amount of time rearing in streams. So as an example of that, kind of in contrast to the previous paper on chum, this paper was looking at, the authors focused on the freshwater rearing capacity of juvenile Chinook salmon, because it's fairly widely accepted that for this species, particularly in the interior Columbia Basin, the limiting conditions occur in freshwater. And oftentimes the question really is, people would easily argue that our ability to influence the ocean is not as strong as our ability to influence freshwater. So oftentimes these exercises are going to focus on freshwater habitat anyways. But in this paper, the authors developed stock recruitment functions of 4 different types for juvenile Chinook abundance as a function of spawners the previous fall. So real quickly, you have 9 different graphs here covering different interior Columbia basins. And in each graph, there's spawners on the x-axis and par, or basically the summer rearing population on the y-axis. And they used, you'll see they've got the Beverton Holt and the Ricker models here, but a couple others, they developed this novel quantile random forest type model. And then sometimes you'll see this other places, it's called a hockey stick model. It looks a lot like Beverton Holt, except it's got kind of more a straight angle up and then flat across. Some of these basins actually provide pretty clean examples of stock recruitment functions, like the Lostine River here, for example. the upper lemhi. So, I showed you the Clackamas example earlier that was quite messy, but sometimes they are a little cleaner. But implicit in this paper is, and they made the assumption, and they go ahead and state this, that they were looking at summer par rearing conditions, that they were assuming that was where the habitat capacity bottleneck occurred. And so this is kind of a new concept I'm introducing here. And so, but it's relevant to carrying capacity. And it's the idea that there's a certain crunch period for each species where the needs of the species are most constrained by what habitat's available at that time. And the idea is that what occurs in this period is what determines the capacity of the habitat for that species. So like in this diagram, for example, and for stream-rearing salmonids, it's often assumed that the freshwater capacity bottleneck occurs in the summer of juvenile rearing. This is a time of year when space is most limited due to low flow, and the metabolic needs of fish are at their highest due to peak water temperatures, which means that the territory sizes of fish are at their maximum. And so like in this diagram here, what's being implied is that in this case, there's plenty of spawning habitat available. And so you could have, tens of thousands or millions of spawners. But what matters is what goes on in this summer rearing period, because this is where the constraint on habitat occurs. And whether you had, in this picture, there's 7 fish over here, whether you had 3 or 7 or 100 fish over here on the left, you're only going to come out with 2 after the summer, right? And then whatever comes through the summer kind of regulates whatever you're going to get at any life stage past that. And the only time this doesn't come into play is like in this simple example, if you only had 1 fish here, then obviously you would just pass 1 fish through. But the idea is that a population that's operating at capacity will hit this bottleneck that really constrains what can occur after that time. But so here's another one of my grains of salt. In my opinion, while there's an intuitive sensibility to this idea, it is a big assumption. And one that's often, in most papers where it comes up or reports, it's often untested because it's often untestable. Empirically determining when a capacity bottleneck occurs, if it occurs, would be an extremely daunting proposition and is likely to be context dependent. There have been a few attempts to try and explicitly address this assumption. So one that I'm familiar with is in this 1992 paper by Tom Nicholson and some other folks that were working at ODFW at the time. They used a habitat-based model to estimate seasonal freshwater rearing capacity of a coastal Oregon stream. So this comes out of that paper. And so in this example, it was the East Fork of Lobster Creek, which is an Alsea River basin. Essentially what they did is they went through they had all sorts of habitat data for this creek. And they had models that basically told them, okay, well, what is our spawning capacity in this basin? And we can get 1.3 million eggs. And then what they would do is they would take an egg to smolt survival and say, okay, well, based on that many eggs, we could get 425,000 smolts. We went through the same exercise with the spring. They said, okay, they had a habitat-based model that helped them decide how many fry the habitat could support, and then, okay, how many smolts would be produced from that. And essentially what they got out of this was they determined that the amount of winter habitat was what was limiting the capacity of this particular stream. So coho redistribute in the winter, typically looking for slow off-channel habitats, can provide food and refuge from high flows. And the implication here was that in this particular creek lacked that overwinter refuge type habitat. But here we run into another challenge or nuance, and this approach tells you the capacity of a specifically designated piece of habitat. In this case, it's East Fork of Lobster Creek. But what it doesn't tell you is what the production potential of a species using that habitat is, because it assumes or requires that you have a closed population, meaning that you don't have any fish leaving this habitat. But what if a capacity bottleneck doesn't result in mortality, but instead in emigration to habitat that does have room to spare. And this definitely happens. This is a diagram from a 2016 paper where Kirk Schroeder and others looked at how juvenile Chinook moved around in the Willamette Basin, and they tried to kind of come up with some percentages of what fish were moving where. But the take home here is that fish were moving all over the place at all times. So when you have fish constantly moving between habitats or consistently drifting downstream and then migrating to the ocean different times, the ability to determine the capacity of a particular population gets really messy. And so relevance of this problem on defining where you're talking about depends somewhat on your question. So it can be quite confounding when you're trying to understand what the maximum population size of a species might be. It's maybe less problematic if you just want to understand what the rearing potential for a given piece of water is. So like in the previous example, if you're just interested in understanding how many fish can we fit in Lobster Creek, that's simpler than asking how many fish can be produced out of adults that spawn in Lobster Creek, because then you have to start to recognize that some of the progeny from those spawners can drift out of Lobster Creek and rear elsewhere. So how is freshwater rearing capacity estimated? I guess maybe before I move into this, I can stop and see, are there other questions that folks have yet?
I haven't seen any pop up, but if anyone does have a question, feel free to unmute and ask that.
Okay. And again, you can always chime in at the end. So
Yeah.
Carry on. So, there have been a lot of different models that have been developed to estimate salmon carrying capacity. If you show me a consulting firm, I can probably show you someone who's developed a salmon capacity model. And part of the reason for this is that often the questions posed are pretty site specific. And so the solutions are too. But I would say, in my experience, there's generally two types of approaches, at least that I'm most familiar with. And the first that we've touched on earlier is the stock recruitment analysis. And so, you probably gathered by this point that what you need is stock data or estimates on the number of parents available in this graph labeled escapement. And then recruitment data for the life stage of interest, whether it's a juvenile life stage or the adult life stage. And this approach is generally used to determine the potential abundance or productivity of a population in an entire basin. The main challenge of this method, though, is it requires long-term data sets. And so there's often challenges with the precision of the input data and accounting for artificial factors that might affect recruitment, such as harvest. And while we're fortunate to have this kind of data in the upper Clackamas, it's not available, for example, in the lower Clackamas, nor is it available in most river basins for that matter. So a second approach that you'll commonly see out there is a habitat-based approach. And really, these kind of involve two stages. And so the first stage is you need to understand how habitat determines carrying capacity. So what habitat factors are important, when, and in what way. And then the second thing you need to understand is what habitat is available. So this illustration or this graphic here is a recent example of a habitat-based method using quantile random forest models. And in this particular model, the authors related stream habitat features to the rearing capacity of juvenile spring Chinook in the interior Columbia. This was the same paper that I referenced earlier with the various stock recruitment curves. But one of the things they looked at is it revealed, at least in the basins they were looking at, relationships between habitat data and the abundance of juvenile Chinook parr in interior Columbia watersheds. And you can see that they ended up hitting on a number of factors related to habitat quantity, water temperature, complexity, cover, and substrate. And these relationships were used to help then define a model that could predict capacity estimates. And they could also use this approach to look at the relative ranking of the importance of all these different variables. So this type of method was useful not only to determine what factors were important, but also which ones were more important or perhaps which ones were more limiting. Just another example that there's a wide variety of habitat-based approaches. This one's a simpler approach, drawing on data from routine habitat surveys, those types of surveys that are commonly implemented by Forest Service or ODFW or any state of the state fish and wildlife agencies. The take home here is that there's a wide variety of these habitat-based methods. And each method comes with its own assumptions, both explicit and implicit, its own data requirements, and its own limitations and advantages. Some common limitations that I have encountered in my work in this type of field is, the first is that applying a habitat-based approach to a reach of stream is quite tractable. But if you want to apply the same method across a watershed, it starts to become more costly and more onerous unless some simplifying assumptions are made. So, it's easy to conceive how a habitat-based method could be applied to the main stem Clackamas between Deep Creek and Carver, for example. It's becomes certainly more daunting if you want to apply it to the entire Clackamas watershed, right? Like, suddenly your information needs and the costs of implementing become much more expansive. A second limitation is not all habitat survey protocols are the same. In fact, no two of them are the same. And you'll typically find that the inputs required by a habitat model may not match perfectly with the data you have available. A common example of this is if you look at large woody debris definitions, they tend to be inconsistent between protocols, even within the Forest Service protocols, between one forest region and another, they can be different. So this can kind of throw a monkey wrench in this approach and potentially require more data collection. I've seen too that sometimes models don't pick up on basic differences between regions. For example, there's water chemistry differences between, for example, Central Oregon streams like the Crooked River that make their productive capacity much higher than nutrient poor streams here on the west side of the Cascades. Anyone that's fished for trout in Montana and also fished for trout in Western Oregon can vouch for this. There's just less primary productivity. And unless this kind of difference is explicitly accounted for in the model, it causes transferability challenges. So a model is really most applicable to the region in which it was developed. And lastly, I touched on this before, but most habitat-based methods are applied to a specific life stage, implying that a bottleneck occurs at that time, and that assumption may or may not be appropriate. So I do want to touch on a somewhat different method, but also habitat-based, and it's called the intrinsic potential method. And this approach really uses landscape features to indicate areas of watershed with high potential for production. So the information is usually widely available from GIS data, from digital elevation models. And since the method's built on landscape features such as stream gradient, valley confinement, and stream width, it doesn't really account for the current in-stream conditions. So it's not looking at what is the pool, riffle, habitat composition, how much wood is in the stream, what's the substrate like. It's really looking at why they call it the intrinsic potential method. And it's basically saying that removing any human disturbance, this is a relative production potential of a given stream reach. It doesn't yield a capacity estimate per se, but it does provide a relative ranking of habitat quality. This example on this slide here is from the Russian River watershed in Northern California, where they applied this method to look at coho juvenile rearing habitat. And it's a nice kind of simple way to quickly look at, areas in red have high intrinsic potential, whereas areas in blue have low intrinsic potential. You kind of quickly zero in on where the most favorable parts of the watershed are to coho production. And then folks have used this to try and inform or prioritize restoration actions. I do want to touch a little bit on the influence of temperature in determining carrying capacity. So in the last 20 years or so, there's been increasing interest in the role that temperature plays in dictating rearing capacity of juvenile salmon and steelhead. There's been extensive research conducted in assessing relationships between salmon growth and swimming performance and temperature. And these have been used by various authors to represent habitat suitability, which in turn translates into efforts to assess the impact of temperature on rearing capacity. And while there's definitely a relationship between temperature and habitat suitability, the exact nature of that relationship is dependent on the species of interest. It's dependent on the region. There seems to be regional differences in what tolerances are. You know, coho in the Klamath Basin seem to have different tolerances than coho in northern Washington, for example. And also just how temperature is measured and indexed. You'll see, one challenge you run into in trying to make apples equal to apples is when you look through all this temperature research, you have various characterizations of temperature data from monthly means to daily max, 7-day average daily max. There's quite a number of ways in which temperature is described, and those differences can pose challenges in trying to translate the meaning of results of different papers. But I would say generally it's accepted that optimal rearing conditions for juvenile salmonids are in the 10 to 16 degrees Celsius range. Definitely that once temperatures begin to reach 20 degrees Celsius, you're moving into very suboptimal ranges there, and habitat suitability declines markedly. So kind of intuitively here then, habitat capacity differences between streams or reaches, or if you're looking at alternative scenarios, you can get at differences in capacity by applying a temperature function like the one shown in the upper right here to temperature data associated with specific stream reaches. So if you had stream reaches with higher temperatures above, say, 16 degrees C, those would tend to have lower, you would predict that those would have lower rearing capacity than a stream reach that has cooler temperatures but equivalent habitat. At a certain point, this information could imply that regardless of the quality of habitat, temperature aside, a reach has very low capacity, at least during the summer, due solely to its temperature regime. And obviously this would tend to occur in the lowest elevation sections of a watershed. So how does all this relate to stream habitat restoration? So one thing is, if you know the current fish, if you know where current fish performance is relative to capacity, that can be informative in determining the utility of specific restoration actions. So for example, if you look at smolt production in this graph, I brought this one back from earlier, smolt production in the upper Clackamas for winter steelhead, if it's below capacity, then restoration actions aimed at improving capacity may not provide immediate benefits. It may be an indication that there's other limiting factors outside of habitat capacity that are currently suppressing the population. And those could be, you may just have too low of adult abundance. You may have some sort of predation issue. It could be a dam passage issue, some issue occurring in the lower river. It might just be that whatever action you implement does not have the intended benefit. And so understanding where you're at relative to capacity can be important in that respect. But conversely, if you understand that you basically are maxing out the habitat capacity of a portion of the watershed, then theoretically changes to that habitat should affect capacity and thereby smolt output. You'll often see that habitat capacity models get folded into larger life cycle models to help contextualize habitat actions. So for instance, this is a diagram from the Shiraz model that was developed for conservation planning. They want to examine how proposed habitat actions may affect populations, or how those effects compare to changes in hatchery, harvest, or hydropower practices. The ecosystem diagnosis and treatment model is an example of another life cycle model. It's got a heavy habitat component that's also been used to prioritize where restoration actions should occur in a watershed. In Washington's lower Columbia River tributaries, EDT has been used to prioritize reaches within different watersheds for their preservation or restoration potential, as indicated. I just pulled this example from the Coweeman River Basin, and you can see they have different reaches from the Coleman River Basin, and this is essentially how they've ranked them in terms of their priority for what they call degradation and restoration. And so the EDT model it includes a habitat capacity function, but also accounts for the full life cycle of salmon or steelhead. In addition to looking at where restoration should occur, tools like EDT have also been used to determine what the appropriate types of restoration actions are. So trying to target restoration to address limiting factors. So this example here, also from the EDT, shows how chum salmon restoration, the Coleman, the actions that increase habitat diversity and reduce fine sediments would have, from their assessment, would have the highest impact for improving chum populations. But it should be said that while potentially powerful, these types of exercises can become quite complex, and then obviously that also makes them more expensive. Another example, trying to get at a similar result as they got with EDT in Washington, the Trinity River Restoration Program in Northern California used a combination of geomorphic and biological models to estimate changes in juvenile habitat capacity that they expected to get from different suites of restoration actions. So they had different ideas on what they might do for habitat restoration, and they ran them through this model, different scenarios, to see what the expected output was. So how does this relate to the Clackamas Basin? I think to start, one thing that's obvious is there's a wealth, particularly with the exercise that Dave Bugney has gone through this last summer. There's a wealth of temperature data out there. I pulled this temperature graph from a 2007 report that I did, where we looked at temperatures in the main stem lower Clackamas. But you can quickly see how, it's pretty straightforward to take a temperature function like this one from the paper in the upper right, and you can overlay that on temperature data from a river reach and look at sort of how temperature affects capacity. And so, in this graph here, as you move from left to right, the maximum 7-day average temperature increases. This is as you're moving downriver. So River Mile 23 here, this point is close to River Mill Dam. This final point here is near the mouth of the Clackamas. And you can see that as you move closer to the mouth, temperatures go up, which are increasingly suboptimal and theoretically become more and more limiting to rearing capacity. And so this type of exercise can be used to prioritize restoration activities that seek to increase summer rearing habitat. Generally, though, it's only going to tell you that habitat projects for summer rearing habitat are most sensible in upper river reaches because, well, really kind of by default, the further downriver you proceed, the more devalued the habitat's going to become. And this type of exercise can be expanded with additional habitat data and more sophisticated modeling. But there's also some risk to this kind of way of thinking. And this was really kind of hammered home by a recent paper by Armstrong et al. And so if you look at this map, and I think this was from the John Day Basin, you can see that habitats in the lower section of this river basin, those particularly in maroon, are basically deemed uninhabitable in the summer based on their temperature profile. And this paper argued that while these habitats weren't suitable in the summer, that the growth opportunities afforded in these reaches in the spring and fall were important to fish production. And so it's kind of an example, a cautionary tale on how a simplified view of habitat capacity could lead to erroneous decisions, such as ignoring habitat conditions and habitats that are just too warm in the summer. And so I thought the authors did a nice job of kind of encapsulating that. And they said that we're not saying that cold water is not important. We're saying that warm portions of basins are also important because they grow fish during the shoulder seasons, and that conserving this habitat is critical for unlocking the full potential of rivers to support fisheries. And so this kind of brings us back, it loops us back to the idea of life cycle models, that this is where more sophistication kind of helps try and capture the benefits of those, like point out in the previous paper, those benefits of growth in the shoulder seasons. But unfortunately, this does make things much more complicated. The models get more data hungry and they get more costly. Going through such an exercise can be helpful though, because it forces folks to define their objectives. It forces people to identify relationships and uncertainties in those relationships, to sort of lay out their assumptions, and also to identify maybe what some proposed restoration alternatives are. But, Paul McElhaney in his 2010 paper pointed this out, is you have to be aware of what I call the octopus technique. That sometimes you'll find, what I've noticed is behind a cloud of sophisticated relationships and analytical techniques lie fundamentally flawed assumptions, which can be difficult to pick out and at some point becomes impossible to determine their significance. So what sometimes happens is that so many assumptions are made clear that it becomes too impossible to determine what their collective import is. So as McElhaney said here, as model complexity increases, it becomes more difficult to trace how imperfect knowledge of internal model parameters, data inputs, or relationships among parameters might impact model results, affecting predictions, subsequent management decisions. And so in that paper, they went on to advocate for the use of stochastic modeling. And the idea of a stochastic model is it helps you to quantify your uncertainty, which, I agree with Paul's paper here. That is the right approach to take, but the downside is it becomes more expensive yet. And sometimes, I have seen these play out. In the end, the type of effort leads you to conclude that the only thing you can be certain of is the vastness of your uncertainty. And that's not a very satisfying conclusion to come to after very long, arduous, and expensive effort. So to kind of wrap this up, so habitat capacity is an ecological theoretical construct with empirical support even in the Clackamas Basin, saying that essentially habitat limits the amount of individuals of a population that can be sustained. Capacity is dynamic and determined by a particular species' needs in its environment. That we imperfectly estimate salmon capacity based on population data or habitat characteristics. We use habitat and life cycle models to ask how our actions affect capacity and populations. And these models are helpful to help make our objectives and assumptions clear, but they also bring their own suite of challenges and costs. And so with that, I can, if there are any questions, I can take questions now.
So Nick, this is Todd. There's a question from Kenneth. Have the temperature adjustment equipment installed on the dams made a difference? And he's referring, it looks like, to the Lewis and Deschutes rivers.
Honestly, they obviously have changed the temperature profiles downstream of those dams, but I've not really been involved in those basins to understand how the temperature changes impact capacity. I mean, I'm sure somebody has asked those questions, but I haven't come across those projects. But it seems intuitive that if you change temperature, you are going to change capacity in some way or another. I'm also sure it's more complicated than you would think at first blush, because you're not just changing your peak temperatures, you're changing, as Armstrong pointed out, temperatures in your shoulder seasons as well. So there's kind of a collective look that needs to be, a holistic look that would need to be taken in something like that.
I have a question here from Bill Monroe. He's curious about the potential benefits to what we're doing downriver from the dam. So we know the true smolts scoot downriver pretty fast, but there may be a high percentage of pre-smolts moving below the dam and then rearing in the lower river and tributaries. So clearly we need some quantitative results to back up our projects.
Yeah, I mean, I could argue how quantitative you need to get. I think it is pretty intuitive that certainly with our new passage infrastructure, we are sending a lot more fish downstream than we had previously, or at least we know more closely how many fish we're sending downstream. But our populations are increasing in the Clackamas, and the more we get in the upper basin, the more juveniles we'll be passing downstream, particularly for coho and Chinook. We pass a lot of juveniles down in the summer and fall period, particularly during the first fall freshets. And my expectation is that a lot of those fish are holding up in the lower Clackamas and maybe the Willamette rivers. Once they pass downstream of here, they're going to kind of eddy out in lower velocity sections of the lower Clackamas. So while projects down there may not be impacting summer rearing capacity, they may be getting more at what's happening in later stages in the life cycle, and perhaps sort of addressing the issue that came up in that Armstrong paper, is that they are providing an area that in the shoulder seasons is an important rearing area.
Yeah, I'd like to open up the mic to anyone. If you want to unmute and ask a question, feel free.
Hi, this is Dave. I just have a question there for you, Nick. On the some of the graphs you were showing, it looked like Steelhead, just as were quite a bit less in the number of smolts or juveniles per adult that were spawning compared to coho. And I'm wondering, is that just a function of the species, or is there certain habitat requirements that Steelhead require that we're not addressing to raise that ratio? Or what's kind of going on there? Any thoughts?
Well, there's probably a couple of different things. One, they are different species. So Steelhead, for example, most of them smolt, so they're going to spend generally 2 summers in freshwater before they emigrate. So they are, right there, even more dependent on the freshwater rearing environment than coho, who would generally rear for just 1 summer in the upper Clackamas. So, the winter steelhead are spending 2 summers up there, the coho 1. Obviously, there's differences in fecundity. They have much different preferences for the types of habitat. Generally, what you'll see is that winter steelhead in the upper Clackamas tend to occur on the, what I would say, the southern or western side of the main stem. So in tributaries such as Fish Creek, Kallawash River, and Hot Springs Fork. Whereas coho are going to be more prevalent on the north, or as you get in the upper river, eastern side of the river. So, you're looking at the North Fork of the Clackamas, the Roaring River, the Oak Grove Fork, Pinhead Creek. So they just tend to, there's obviously overlap, but they tend to occur in different parts of the watershed. So obviously then there's different habitats available to them. Does that answer your question?
Yeah, I think so. I guess what I'm getting at is that, I was doing some research and looking back at old newspapers. I found one back from 1907 for Eagle Creek. And back then they had actually trapped, steelhead going up Eagle Creek, and they counted them, and the point of which was to send eggs to the hatchery at the time. I think it was on Clear Creek or whatever. But anyway, the point is that at that time they had counted in 1907 almost 11,000 steelhead adults coming up Eagle Creek, which is probably as much or more than exists in the whole Clackamas River Basin now. So I'm just wondering, trying to get my arms around what has changed, with regards to steelhead, that particularly in the Eagle Creek watershed, that we could try to address to maybe increase that, that return, because right now it's been heavily hit.
Yeah, I'm sure there's no simple answer there. I don't think it'd be hard to argue that the habitat capacity has changed significantly. The genetic background, the legacy genetics of the fish are different now than they were in 1907. And probably the ocean conditions are different now than they were then. I think probably anything you could think of is going to be a contributing factor, but we would have to have absolutely shocking ocean survival at this point to get 11,000 adults back to the Clackamas as a whole, much less just Eagle Creek.
So Nick, there's another question on the chat, comes from Scott. How much do the habitat requirements of different species change the carrying capacity of a stream?
I guess you're gonna have to clarify the question for me. Not sure what you mean. Go ahead and.
Scott, go ahead
Scott.
and unmute.
Well, what I'm getting at is it seems like there would be competition by different species for the various habitat. It seems like that would really confuse fish counts and how well they survive.
Yeah, I won't say that I have an answer for you on that, but it does seem intuitive that you have high densities of all species, that they are to some extent using each other's resources, right?
Right.
And so there's going to be some, these graphs show density dependence within a species, but I wouldn't be surprised if you could find an example where you can illustrate density dependence between species. You get other issues too, unrelated to just habitat capacity. But for instance, we see, in our traps all the time, coho, particularly coho just before they smolt and steelhead just before they smolt, absolutely gorge themselves on fry. So, you can get species consuming their co-occurring species of different life stages. And so clearly there's a lot of interactions that go on between species, but you also, kind of the other side of it is the more fish you have back, which pushes you towards capacity, you're also getting more marine derived nutrients back to the system, which, theoretically should help to boost the capacity of the system by sort of, just boosting the primary productivity.
Thank you. Thank you.
Anybody else care to unmute themselves and ask a question?
I mean, these are the kind of head scratchers where you could talk for days about interactions and data gaps and
Well, and I'm afraid that
methodologies.
I probably didn't provide a whole lot of answers. I probably gave people more questions, but it should not be overlooked that this is all complicated stuff. And despite the fact that fish biologists have been around for over 100 years, we still don't have a great grasp of a lot of this, and we're closer than we've ever been, but the knowledge base is still quite imperfect, partly because everything is so darn variable and hard to study. There's many moving parts.
Yeah. Well, I want to say thank you very much, Nick, for taking the time to put together this excellent presentation and sharing your knowledge with all of us. And I'd like to, offer up to anyone to stay in touch with Nick if you have follow-up questions from this. So thank you. In closing, our next session will be on December 14th at 6 p.m. And the Fish and Water series continues. So we're going to have an overview of fish hatcheries within the Clackamas Basin. You can use the same Zoom meeting link and you're already registered. So we'll send a reminder email the day before. And we'll also send a thank you email to everyone who's registered, as well as a link to the recording and more information about getting continuing education units from Clackamas Community College. So thanks again, Nick, for the wonderful talk. And we also want to thank our gold sponsors, Oregon Beverage Recycling Cooperative, Clackamas Water Environment Services, and our bronze sponsors, the Clackamas River Water Providers, Metro, Port Blakely, and the Geological Society of Oregon Country for helping us keep this conference free for everyone with their support. So every little bit helps. So if you like what you see, please consider a small donation. And thank you for joining us again today. Please let us know what you thought of the program, and we'll see you 2 Tuesdays from now on December 14th. Did I forget anything else, Todd?
You covered it.
All right.
Thanks, Liz.
Yeah. Thanks, everyone.